Hello, I'm Professor John Kelly, and this is the Weber Auto YouTube channel. Today we will be looking at the charging system for the 12-volt battery, also known as the auxiliary battery, on a 2016 and above Toyota Prius. Now, this particular model I have right here is a 2017 Toyota Prius Eco, but the 2016, 2017, 18, 19, and the Prius Prime all use the same basic 12-volt charging system. So under the hood, finally on this fourth generation Prius, we have the 12-volt battery rather than being in the back of the vehicle hidden away under some compartment. Although this battery is under the hood, it is still a unique sized battery. As you can see in this photograph here, it has the letters EN, which indicate European normal size battery. So this still is not a battery that you're going to be able to just find at any auto parts store. Although it is just a lead acid battery, it is not an AGM, absorbent glass mat battery. Okay, so let's take a look at the parts of the charging system that keep this 12-volt battery charged on this vehicle. Now, the 12-volt system is totally separate from the high voltage system on this car, and as a matter of fact, almost the entire vehicle runs off of the 12-volt system. But I think you'll be surprised as to how much current does this battery actually supply to run the low voltage systems on the vehicle. Now, another part of the charging system on this vehicle that we can see the top of it right here under the hood is the inverter with converter assembly here. And if we look right on the front of this inverter with converter, right here, there's a stud sticking out. That is the DC to DC converter positive output terminal. So the DC to DC converter that's inside the inverter with converter assembly on Toyota Priuses connects to the high voltage battery in the back of the vehicle when the ready mode is on, and uses that high voltage, steps it down to a lower voltage, right around 13.5, 14 volts, and uses that to charge this 12-volt battery and to supply electric current to the rest of the vehicle's 12-volt system while you're driving down the road. There's a maximum output on most of these DC to DC converters of around 100 amps, and it's a really bad idea to use any hybrid or electric vehicle to jump start another vehicle, especially if the ready mode or the ready light is on. It needs to be off if you must use it, but it's a real bad idea to do so anyway. Okay, so the charging system for 12-volt battery is the positive terminal right here, rather than having an alternator, a belt-driven alternator connected to the engine. And then the ground is just simply bolts that hook to the metal housing of the DC to DC converter and inverter assembly here. So what I have here under the hood are three different Fluke 87 Series 5 multimeters. And one of them we will hook up to the 12-volt battery. One we will hook up to the output of this DC to DC converter and measure how much current it's supplying. And then another one will measure the current going into and out of the 12-volt battery. So let's get those hooked up. So let's connect a Fluke 87 Series 5 multimeter to this 12-volt battery. I'm going to turn it on and hold in the yellow button, which disables the power off feature. It automatically goes to sleep after a little while. I do not want it to do that during this demonstration, so now it will stay on until the battery goes dead inside the multimeter or until I shut it off. Now, obviously we're going to connect the red lead to the positive terminal and the black lead to the negative terminal, and I'm reading 12.83 volts. Now, while we are here, this 12-volt battery on the positive terminal and on the negative terminal has a whole bunch of other things connected to it. So on the positive terminal of the battery, we have a big heavy wire coming from that DC to DC converter that we just looked at. The positive output terminal comes right over here, and it does not connect directly to the battery positive terminal. Instead, it connects to what's known as a fusible link block. Now, this fusible link block has 4 different fuses inside of it. It has a big 120 amp fuse that protects the DC to DC converter circuit as it connects to the battery and the rest of the vehicle. And I believe the DC to DC converter maximum output is right around 100 amps. We will try to stress test it here and see if how high we can get it. Then there are 3 other fuses that connect here. 2 of them go to the underhood fuse block, junction block with the relays and fuses, and then 1 of them goes to the electric power steering. These are all high current fuses. I think there's a 60 amp fuse and a 140 amp fuse that feed the underhood junction block, and then an 80 amp fuse for the electric power steering. All right, so that is the positive side of the battery, but here on the negative side we have a battery sensor, and this is a smart sensor. It's actually connected over a data line to the hybrid control ECU over the LIN bus. It calculates how much current is leaving the battery, it measures the battery voltage, it calculates the battery state of charge and the battery state of health. So it's a smart sensor that is used to fine-tune the output of the DC to DC converter so that we're not wasting energy, and so that we keep this 12-volt battery in really good shape for powering up the vehicle in the accessory mode and to bring the vehicle into the ready mode. All right, the next multimeter I'm going to hook up, I have a current clamp connected to it from Fluke. And I'm going to turn the Fluke 87 meter to the millivolt setting because that's where we need it for the current clamp. And we'll turn on the current clamp. There's a dial on the front of the current clamp to 0 the meter. So we just turn that dial until it reads 0. And now we are ready to measure current. So I'm going to connect this current clamp to the Fusible link block in between the positive battery terminal and the Fusible link block itself. There's just a flat piece of metal there that's covered with plastic to insulate it. There's a direction of current arrow here on the current clamp that faces away from the front here, so that'll measure the amount of current leaving the battery itself. So I will point that arrow away from the battery positive terminal. Okay, then I have one more Fluke multimeter that I'll put on millivolts with another current clamp. We'll turn it on and get it zeroed. And this meter is going to tell us how much current the DC to DC converter is supplying to the rest of the vehicle and to the battery at the same time. So I'm going to clamp this around the cable going from the DC to DC converter to the positive side of the battery through the Fusible link block. Okay, if we go through the official Toyota on-vehicle charging system inspection, it takes us through the following steps. We check the auxiliary battery, make sure the cables are connected to the correct terminals, make sure that there's no damage to the battery, and make sure that each clamp is torqued to specification. And then it tells us to check the auxiliary battery voltage. And then it tells us to turn off the vehicle power and turn on the headlights for 30 seconds to remove the surface charge from the auxiliary battery. So the headlights are on, we just need to wait. We were at 12.86 volts, we're down to 12.53. It looks like we are pulling 4.2 amps of current out of the 12-volt battery to run these headlights. By comparison, the second generation Prius I was playing with yesterday draws 18 amps of current for its headlights. All right, our 30 seconds is up. So if the 12-volt battery is above 12.0 volts and we are reading 12.74, then the battery is considered good enough to move on to the next step of the diagnostic. If it's not, then they want you to recharge the battery and test it again. Then, once you've done that, they want you to check the connection at the DC to DC converter. That stud that was sticking out of the DC to DC converter, the 12 to 14 volt stud, If the nut comes loose on that, like a loose battery cable, then you'll get a voltage drop across there. You'll get some corrosion and arcing and so on. They want you to make sure that that is clean and tight and torqued to specification. So if that's okay, which this one is, then we move to what's called the DC to DC converter function test. So that tells us to connect an amp probe like I have here on the battery to measure how much current comes out of the battery. And then it tells us to turn on the power switch, take us to the ready mode, and leave the vehicle until the current flowing to the battery becomes 10 amps or less. Now right now we are showing a negative 0.8 amps on our 12 volt battery output amps, and that means that's current going into the battery. So if we get a negative number on that center multimeter there, that's current going into the battery. If we get a positive number there with no negative symbol, then that's current leaving the battery. So let's look at that one more time. I'll turn the headlights on. So right now we have a positive 4.1 amps leaving the battery. Notice there's no negative symbol. I turn off the headlights, and now we get a negative 0.6 amps, so that's current going back in to the battery. Okay, so what they want us to look for one more time is they want the current flowing into the battery to be 10 amps or less when we power on the vehicle to the ready mode. So I'm going to bring this to the ready mode, and let's take a look at whether or not we're putting current into the battery or taking current out of the battery based on the polarity of that multimeter reading. So here I'm going to ready on the vehicle. Okay, I've now readied on the vehicle. You can see the current going into the battery is 10.8 amps. And that means our DC to DC converter is charging the battery. If you look at our voltage there, we have 14.01 volts. The meter on the far left there is the current output of the DC to DC converter. So if the current output is 23.8 amps and the current going into the battery is 9.7 amps, then there's almost a 10 amp difference. So somewhere we have 13 amps of current being used that is not going back into the battery. And that's because we've powered on the vehicle. We've got all the onboard computers powered up. We've got the instrument panel powered up. We've got everything turned on and activated. And if the DC to DC converter is working as it should on any hybrid or electric vehicle, it doesn't have to be a Toyota, then the DC to DC converter should always be able to supply current to the battery in addition to powering up everything else that's on the rest of the vehicle. So we're below the 10 amps that they wanted us to be, and so now the rest of the DC to DC converter function test tells us to turn on the high beam headlamps, turn on the blower motor to high, and turn the rear window defogger on. So we are trying to put as much electrical load on the DC to DC converter as possible, and we will see the DC to DC converter current go up. Right now we're only at 20 amps, but we'll see that go up considerably. The current going back into the battery is 8 amps, and we're at 14 volts where we were at 12.8 or 4 or 3, whatever it was before. So let me turn on the blower, the headlights, and the rear defogger. Okay, so here comes the headlights. It looks like it won't let me go to high beam because it has automatic headlights. All right, next is the rear defogger. Okay, that's the defogger. And now here's the climate control with the fan on high and the eco mode turned off. Okay, The internal combustion engine has started, but that engine only starts to recharge the high voltage battery, and that high voltage battery is what feeds our DC to DC converter so that we can charge the low voltage battery. So it doesn't matter if the engine is on or off, the DC to DC converter is still going to work as long as the high voltage battery has a sufficient amount of charge to enable it to work. So notice we've got 58 amps of current leaving the DC to DC converter. We still have 5 amps going into the battery. So out of those 58 amps, 53 are being used somewhere on the vehicle, and we are at maximum load other than the high beams being on. We could put more load on it by getting the cooling fans to come on if the engine were to get the coolant in the radiator hot enough, or in the engine hot enough. Also the electric power steering. I'm going to turn the steering wheel. Let's see if that makes any difference. So you can see the engine shut off. That really doesn't matter. Here's the steering wheel moving now. Now, with the maximum loads of everything 12 volt that you can find to turn on in the vehicle, we should get at least 12.5 to 15 volts output. We're getting 13.93, and we should also have 0 amps or less leaving the battery. Well, we have 4.8 amps going into the battery. So our DC to DC converter is working just fine. This is a far superior charging system check than just throwing a multimeter on and seeing if the voltage comes up. Because voltage coming up doesn't necessarily mean that you've got good connections and a good DC to DC converter that can supply enough current to keep your battery charged. Also, keep in mind that batteries go bad. A typical battery after 5 years is pretty much going to die, especially when cold weather hits or super hot weather hits. So this basic DC to DC charging system check, once again, will work on the 2010 Prius right behind me, the 2004 right behind it, the 2002 right behind it, the Chevrolet Bolt right across the shop over here, the Chevrolet Volt right next to it, the Prius Prime on the other hoist over there. They all work like this. The amount of current might be different that it's rated for. For example, the Bolt and the Volt, I think, have a 160 amp output versus the 100 amp that we see here. But as far as being able to load everything, turn everything on, and make sure that the DC to DC converter is still providing maximum output is the same. Now, there's one other thing about this charging system on the 2016 and above Prius that you need to know about for those of you who have that vehicle. It actually has 2 different modes of operation. One mode is where the hybrid vehicle control ECU tries to control the charge rate and voltage, and it varies it based on the actual needs of the system as you drive, and that is called charging control. The other mode that it goes into is called constant voltage control mode, and that's where it just outputs a constant voltage, and it does that when the auxiliary battery is low on charge, when it has extremely low or high output temperature, when the cooling system in the inverter converter is indicating that it's really hot and there's high electrical load on the DC to DC converter, if there's a battery sensor malfunction, if there's a LIN communication line, the data line failure, it'll go high. And if you've been driving for at least 20 hours straight, in other words, you haven't powered off the vehicle in 20 hours, it'll also go into this constant voltage control mode, or if there's a voltage sensor failure. So basically there's 2 modes of operation. One is variable based on the needs of the vehicle, which is more efficient. The other one is if there's super high loads or any types of problems in the systems, it'll go to a constant voltage output to try to keep up with demands. All right, well, that is the charging system check on the 4th generation Prius, 2016 and above Prius. Thank you for watching.